Okay, let me show you another example of deriving Lewis structures using my shortcut. Now, for this example, so I'm going to now focus on the elements that are farther down the table. So elements that are below the second row, right? And specifically, I'm focusing on the elements here on the P block. So any of the elements below the second row have one specific feature associated with them. And it's the fact that from that point on, you're looking at energy levels that are equal to 3 or higher. And I'm going to just look at n equals 3 because this will kind of set the premise for everything else that follows. Uh, if n equals 3, meaning that you're on the third row or below, the value of L could be 0, in which case you're dealing with an s orbital. Or the value of L could be 1, in which case you're dealing with 3 sets of p orbitals. But the value of L can go up to n minus 1. And since n is 3, L can go up to a value of 2. And for 2, we're dealing with a set of 5d orbitals. And what you can see right now is that you actually have a total of 9 orbitals available in the third energy level. And what this means is that elements that are below the second row have enough space available to accommodate more than 8 electrons. The octet rule is only crucial to follow for second row elements because they don't have enough orbitals to accommodate extra electrons. But third row elements, fourth row elements, fifth row elements, sixth row elements, they have more than enough orbitals to have more than 8 electrons. And so what this means is that if your central element happens to be a third row element or below, you can violate the octet rule. You don't have to, but if the situation arises such that it's best for you to break the octet rule, as long as you're at the row element or below, and that element is central, you can break the octet rule. Okay. On the other hand, if you have a third row element or fourth row element, but you're an external element, you will still abide by the octet rule. You'll see that in a second. All right, so let's take a look at sulfate to kind of exemplify this process. All right, so sulfate, if we focus on the structure, we notice that the element present in the least amount is sulfur. It also happens to be the element with lower electronegativity, but the fact that it is the element with the lowest amount and it's not hydrogen um, pretty much sets them up as being the central element. What that also means is that the 4 oxygens of sulfate will have to be surrounded or surrounding rather sulfur. Okay, just the way I depict it right here. Now, with that skeletal framework in mind, we move on to the next part, which is to determine the number of bonds arising from this external element towards the central one. And oxygen is in group 6. So 8 minus 6 tells us that we need to have 2 bonds on oxygen for it to be neutral or to have a formal charge of 0. So we draw double bonds from each oxygen towards the central element. Notice that none of the oxygens have any other connectivity to any other atom. So here it's safe to just write the double bond directly onto the central element. All right, now, if you look carefully, you'll realize that you have a 2 minus charge on the structure. And that means that we have to come up with a means of having that 2 minus charge overall in this structure. And the way we do that is by decreasing the number of bonds. That's how we're going to arise with the negative charge that we see on the structure. So we want to ultimately come up with a 2 minus charge, which means that we have to decrease the bond order by a value of 2. But if you take one of the oxygens, it doesn't matter which one, and you decrease the bond number by 2, you will break the connectivity altogether. So what you want to do is to break the connectivity partially for one oxygen and then do the same thing for a second oxygen. In other words, you could take the oxygen here on top, reduce the connectivity to only one bond, automatically the charge goes down to -1. Do the same thing with a different oxygen, doubly bond the oxygen, decrease its bond length, or rather its bond order by a factor of 1, and you will decrease the charge of that oxygen by a factor of 1. And now you have come up with an overall 2 minus charge on the structure. All right, now, looking at the central element, we first notice that, okay, sulfur is not a second row element, so we do not need to worry about the octet rule. If we violate the octet rule, it's totally fine. We don't need to, be concerned with it too much. But it is important that we do verify that the central element is not a second row element. What we do now is determine if there's any electrons, any valence electrons of sulfur that haven't been accounted for by drawing the different bonds. So we subtract number of bonds that we currently have on sulfur from the group number of sulfur itself, and sulfur is in group 6. And if we count carefully, we'll notice that we have 1, 2, 3, 4, 5, 6 bonds around sulfur. So that tells us that we have no electrons, no valence electrons of sulfur unaccounted for. So we basically leave sulfur by itself the way it is. Nothing to be done there. All right, the final thing is to complete the octet of the external elements. And in order to do that, we simply count the number of bonds that each one of them has. So if we look at the doubly bonded oxygens, we have 2 bonds on the oxygen. Each bond has 2 electrons. So currently, doubly bonded oxygens have 4 electrons on it. And that means that we're missing 4 electrons still. So we'd write the 4 electrons as 2 lone pairs, as shown right here. For singly bonded oxygen, we only have 2 electrons currently on each one of those oxygens. So we're missing 6. And we basically draw the 6 missing electrons as 3 sets of lone pairs. And the moment you've done this, you have arrived at your final Lewis structure, the Lewis structure for sulfate. Okay, now I'm gonna introduce you to this idea of resonance structures since we're talking about sulfate, but I'm gonna give you a separate video where I show you a little bit more meticulously how to do this. But resonance structures kind of have this feature. Pretty much the idea is that when you draw a Lewis structure, there might be different ways of drawing the same thing, meaning that your double bonds and your single bonds in your sulfate ion could actually be kind of shuffled around, right? Just the way in which I selected the top oxygen and the bottom oxygen to be singly bonded, I could have done the same thing with the left and right oxygens, or I could have used some other permutation, and all of them would have been the same thing. 2 of the oxygens would have been doubly bonded, 2 of the oxygens would have been singly bonded. Now, a different way to look at this is that if you have a structure where you have a central element that has a multiply bonded connection to some other atom, and in addition to that, there's another connection to a separate atom that has lone pairs. What can happen is that the X element here with the lone pairs, which is singly bonded, can have its electrons dumped onto the central element. And at the same time, the electrons from the doubly bonded Y element get out of the way. It's kind of like a windshield type of motion that basically give you this overall process. And now notice what's happening here. The X element here goes from having a single bond to now having a double bond. So you increase the character of the bonding, so you end up increasing the charge of the element. Before it was neutral, now it has a +1 charge. The Y element used to have a double bond, now it has a single bond. You decrease the bond order of that element, and since it was neutral, you have now decreased its charge to -1 value. Now, this may be more important for further chemistry courses you may take in the future, but something to keep in mind. If it so happens that the central element has less than 8 electrons, so it's electron deficient, and you have elements that are bound to it that do have lone pairs, you could have those lone pairs donated to the electron deficient center, either from the Y or the X, to basically create a resonance structure. And since E has no charge to begin with, the moment it receives extra electrons, it will have its charge decreasing to -1. Whereas the Y's that are kind of giving away the electrons, or the X that's giving away the electrons, being neutral to begin with, they develop this positive charge. So, something to keep in mind. The other thing too is that if you notice this, the overall charge of E, the total charge of the overall structure here is neutral. And by the time you get to the structure right here, you have +1 and -1, which also neutralizes, gives you a neutral charge. And this, at the end of the story, whatever happens here in terms of formal charges has to equate to the overall charge of the molecule. Now, if you're having difficulty coming up with this +1 or -1, the best approach is to use the long formula Formal charge equals group number minus number of bonds minus number of non-bonding electrons, and that will always give you the proper formal charge for each individual element. All right, so before I get into resonance structures, I'm going to stop the video right here, kind of, to prep you up for it. And in the next video, I'll show you a few examples of resonance structures.